So I'm going to start right now our new probably chapter, and it's not about beam behavior, rather than it's about beam design, and I have a presentation for you guys. So let's go ahead and close the assignment. Don't save. Let's go ahead and close this past presentation, and here we go. We have to start today our beam design. Just need to remind you that there are two processes called beam design and beam check. Let me ask you, what we have done so far in my class, is that design or check? Any help?
Check.
Thank you, sir. It is a check because if you look at the last week through the 3 classes, the beam is totally given to you with all concrete dimensions and rebar. And your question is how much this beam can handle. What is the beam capacity? Right now, we're shifting from beam check into a beam design. And you can see the process is reverse. And you've seen this picture before. So the picture on the right is not new. Probably I need to zoom in a little bit. So guys, this picture on the right here is a typical cross section of a beam, where on this cross section I show all the beam design elements. The width of the beam, the height and main reinforcement, the cover, the spacing, the skin reinforcement, the stirrup hangers. So all those are your beam design elements. And you will see the slide is very, very much like when I introduced for you the same slide, but I kind of rewrote it, reformulated in a way that leads us to understand what do we mean by beam design. Let me tell you, in beam design, the requirement of the beam is given. So this beam, it's supposed to stay safe under acting load. However, when we start the design, we know nothing of this picture, zero. We don't know what should be the beam depth, or what should be the beam width, or how much steel. All those elements are unknown. The only thing that's known is we want to come up with a beam that can survive the load. That's what we know by this moment. So we know the loads because you guys have seen that, huh? You are able to determine what is the load, what is the live load, what is the snow load, what is the bonding load. So you can find the loads. And if you know the loads and you know the span and the structural system, you can find bending moment and shear and axial force using SAFI. And we are now at the design, which means we're going to find all those elements that is able to or are able to resist the bending moment safely. Now, let me iterate with you guys the elements. So you can see here, we have the first thing called concrete dimensions. Concrete dimensions, I give them here green. And as I said, guys, anytime you see a color, it has a message. It's not just random colors. What you see here on my slide, those are messages for you. Okay, and I'll share with you how and why, what not soon. So the beam width, which we always use letters lowercase b, beam width. I said here the beam width is one of the design parameter, and again, you guys can think of it as unknown for now. But the thing is it really unknown? Like in mathematics, when we say unknown, it means completely unknown. That's in mathematics, huh? It is unknown. It means we don't know. It can be anywhere from minus infinity to plus infinity. That's the meaning of unknown in mathematics. But the thing is my width of my beam is completely unknown, so it can be from minus infinity to plus infinity. The thing is, it is not. Okay. So guys, the beam width, it cannot be negative, and you guys for sure know why. Yeah? It cannot be negative because it's a distance, the dimension. And we cannot build a beam like the width of the beam is 5 centimeters, like 50 millimeter, okay? And I will share with you why soon. But the beam width here starts from 200. So the minimum that we can build is a 200 millimeter width. And it goes with interval 50 millimeters, so we can choose the beam width to be 200 or 250 or 300 or 350 and so on. Why 200 minimum? Let's zoom in at the bottom of our beam and see what do we need to fit in my beam. You can see any beam, it's a must. We must have cover from each side. The cover, it depends on the durability requirement. And then we need a stirrup, so that's 10 millimeter, 10 millimeter. And then we have at least, look at this please, at least 2 bars. Because every corner of a beam needs a bar, which means minimum 2 bars. And between the 2 bars, there should be a spacing because it does allow concrete to flow. If you put all this in one package, you will know, no, I cannot make my beam 50 millimeter because you think minimum cover is 30, so 30 plus 30, that's 60. And then steer up 10 millimeter, so 60 plus 10 and plus 10, so we are at 80. And if I add 20 m, so 20 plus 20, that's 40 plus 80, it's 120, and leave some spacing. And I can tell you from my experience, we tried our office before, tried to build the 200 millimeter beam, and it's ugly because simply the contractor cannot do that right. It's very, very ugly here because you have to do a radius here, okay? I can tell you practically this 200 is 250 millimeter. Anyway, so you know, by the way, the beam width is typically it's given by the architect because you think about under this beam there should be a wall, and what do you think the beam width and the wall width? What do you think? They should be different or the same? The beam width and the wall width. If there is a wall below this beam, just like so, what do you think? Should we have a different beam width, or it has to match the wall thickness? What do you think? Any idea?
Same.
Same, okay? Because otherwise it will look ugly, huh? If I move this line, I put it here, so your wall ends here, okay? And then your beam is narrower, then it looks ugly. So typically the beam width will have to match the wall thickness. So that's why I sit here and I can see there is a reason for putting this as green, because simply it is not unknown. It is either given to me by the architect or can be assumed with a reasonable minimum of 250 and with increase of 50 millimeter interval. If it's up to me, if the beam is exposed, then the architect will control it. If the beam is hidden, which nobody will see it, then it's up to the engineer. But you have to be reasonable. We cannot make a beam 150 millimeter or 100 millimeter. Okay, so that's the beam width. Let's try to do the same discussion on the beam height. You can see here it's in green, which looks like you can extrapolate and you can know that this is given by somebody. So the beam depth has interval of 50 millimeter, 50 millimeter, and typically this concrete dimension are defined by architect or selected by engineer. Okay. You will see, not today, but next class, you will see if the architect doesn't provide any help for the H, for the height of my beam, then there are some tools that we can find the H. And guys, remember, I'm asking you, the H is connected to what? Like, primarily the H is connected to the span of your beam. Whenever you have larger span, then the H will have to increase. I'm hoping that you guys by now understand why. I do not run the discussion, but H is connected to the span of your beam. Whenever the span is larger, then we need a larger depth. Okay? Hopefully you know why that. It's very important. Think of it. Why the H is connected to the span of the beam. Now, the thing is, guys, in our design, do we use the H or the D? Again, remember, what's H, what's D? Let's look at this slide here. So H is the overall thickness of my beam from top of the slab or top of the beam to the bottom fibers of my beam, while D is called effective depth, which is simply from the centroid of the group of the rebar to the same point top of the slab. Which one was used in my check? What do you think? Anybody, any help? Which one is used in my beam check?
The effective depth.
The effective depth, that's correct. Okay, so the effective depth, this one here is used in the check, and you can see it's also used in the design because look at the name, it's effective because that's simply function of the lever arm. The more D, we have more lever arm. Okay, H can be anything. However, D, it is the main factor drives the design or the check. Now you can see if the H is known, and you can see because it's known, so I put this one here in green, So let me ask you, why do I say that D is unknown? Anyone is following? The H, the height of the beam, will be estimated either given by the architect or estimated by the engineer, the designer. So which means green, it means known. So why I rewrote this one? I said the effective depth is unknown. Any help?
Because we have no idea how much rebars are we going to put in, and what is the spacing of our rebars, and what is the cover that we have to put in.
You want to get 5 marks for that?
Thank you.
Okay, so true, as Jelly said, the effective depth of the beam is not known. Even we know the total thickness or depth of our beam, because simply you can remember this is something probably you've done. You're trying to do this like 10 minutes ago when I gave you this extra question. The D prime is the D prime. Look at here. So the D prime is simply from the centroid, not to the top fibers, but at the bottom fibers. And since when we say design, it means this is unknown. We don't know how many bars. I don't know what is the bar diameter. I don't know if I have one or two layers. And since this is unknown, when we do the design, it means the D prime is also unknown. And that's why at this point of time, the D or the effective depth of the beam is unknown. Okay. You can see I wrote this one here. D prime is unknown because rebar layout is unknown before finalizing our design. Okay. Now, how about the other things which it doesn't show in my concrete section here? The F field. Does my check was dependent on the F field? That's like the yield strength of my rebar? Yes or no? Does it? When I estimate moment of resistance of my beam, does it depend on the yield strength of my rebar? Does it?
Um, yes, I think.
Yes, it does. Thank you so much. Next is, does my beam resistance M sub R, does it depend on my F prime C, which is concrete compressive strength? It does. Okay, guys, remember that it does. It does depend. And you can see in my design, as I said, we're not only supposed to find concrete dimensions and how many rebars, but also we need to talk about what should be my strengths of my material, like the F sub Y and F prime C. However, you can see here, I put them in green. What does it mean green? It means they are known. How come they are known? I'll give you the answer. The answer is, since we are in Canada and we simply use probably three kind of rebar and one is the most found in the mill, then we know that this number is 400. So it is not really a mathematical unknown like the one used last year in XYZ. Huh? This is different. This is strength of material, and it's not really an unknown that can go from minus infinity to plus infinity. We have very specific grades that we must pick from, and one of them is the most popular, most made. So in our design, we use it. We use F field is equal to 400. How about F prime C? F prime C, which is concrete compressive strength, is completely unknown. Can it be from minus infinity to plus infinity? You guys know that, huh? Any CVT students will know that. It's not really completely unknown. We have a range. We always make our concrete between 20 and then 40. Less than 20 is for non-structure reason, like a filler. Above 40 is very dangerous because simply there is lots of problems with the shrinkage and cracking. So we typically made it out of 20 to 40. And so how we handle this unknown process, we just started from something that's reasonable, right? Typically beams, they are made out of 25 MB concrete, or maybe 30, and columns because they have higher loads. So we typically build them from 34, 35, and 40. And the way we do it is we do it iteratively, which means we start from the 25, and if it doesn't work, I can simply modify my design a little bit and change it to 30 and see what happens. Okay, and then finally you will see the only so far we have two red colors. Look at this, please. So look at my slide. Looks like I have two red colors. One is my D, which is the effective depth of my beam, and then the others, or the second unknown is AS, which is how much rebar should I place in my beam. So far, although we started from so many unknowns, including concrete dimensions and material properties and area of steel. But finally, after we had this discussion, I'm hoping that everyone in the class knows that so far we have two, namely the effective depth of the beam and the area of steel required to resist a given bending moment. Okay, are you following so far, guys? Are you following? Can you make some noise?
Yeah, we're following.
Okay, thank you, sir. So let's move on to the next slide. And the next slide here, I'm asking you guys, is this slide new for you? Take a few seconds. Is that new for you, this slide here? Look at the sketch and what I wrote in this slide. Are those new or the same exactly what we've
They're
done
the
before?
same. They're the same.
Nothing new, huh? We're starting here our design from the equilibrium equations. Sigma, the forces in the x direction equal to 0. Remember, huh? This happens no matter what. It's tension, compression, or balanced. No matter what, if you have a banana on your beam or your beam is about to fail. Doesn't matter. At all the time, there should be a balance between the force, compression force in concrete, and then total tension force in rebar. Please, huh? It is not only in tension or compression, or it's every time, all the time. There is a balance. Also, what happens here is, you can see I said sigma fx equal to 0. So T sub r is equal to C sub r. And we replaced the T by the equivalency, which is stress times area. And concrete is also stress times area. So we have this equation here. Next is, what's my moment? So sigma moment equal to 0, which means if you take the moment around the centroid of the rebar or the center of the concrete compression, then you will get these equations. So the MR equal T sub R, total tension, multiplied by lever arm, and then MR equal to total compression multiplied by lever arm. And you can simply replace the T sub R by the equivalence, okay, which is the stress times area, same here. So you can see nothing new, zero new. Okay, now before I start, you can see this equation is what we used over last week. Last week, we came up with this equation. Now let me ask you. Now we're not checking, Remember, we've done this in the checking process. When we check the problem, check a beam, we simply have to figure out the M sub R, which is beam resistance or moment of resistance, which we call it beam capacity. Now, when we do a design, do I know the MR? Please focus, when I'm doing design, do I know the MR or I know some other moment? What do you think?
When you do the design, you don't know the MR.
Anyone else has a different input? Anyone else? My question is not very difficult. I'm asking you, when we do a check, so we have the beam with all the information, we're able to find the MR. And then if we want to say that the beam is safe or unsafe, then there is another moment called MF, which is the factor of the moment of the acting loads. And for my beam to be safe, always the MR should be more or equal than my MF. You guys agree? Show your hands if you agree. Looks like you guys, you are so shy. Okay, thank you. That's enough. Thank you. Put your hands down. Okay, now, so you can see here, that's what we do in our check. But for the design, we know when we start the design, we know the MF and we don't know the MR. Okay, because the beam does not exist at the moment that we start our design. Please, guys, please, this is very important. Please make sure you understand this statement, please. Okay, take your time, read those things. In structural design, whether steel, concrete, you will always see something called MF and something called MR. There is something called VF and something called VR. There is something called BF and BR. Those are the moment and the shear and axial force. Okay? In general, whenever you see R, it means resistance. It means capacity. It means maximum bending moment that this beam can handle. Regardless what's the applied load, regardless what is the applied load. You following? Now, so what's MF? MF is the maximum factor bending moment applied to your beam under the effect of factored load. Need to remind you, where do we get this one? We have to make load combinations, just like what we did on SAFI. Very important, guys, very, very important. People are confused. They don't know the difference between MR and MF. MR is the beam capacity, regardless the applied moment. It can be a banana, or it can be a bridge, or it can be anything, like trucks. Sorry, the load trucks. Okay. However, the MF is the acting bending moment under factored load from different load combinations. Okay. If you follow, please show your hands quickly. Okay, that's enough. Thank you. Okay. Now, in our design, to make a safe design, we've said this several times before in my class. We said in our design to be safe, this condition here has to be satisfied. Always, the beam has to have extra capacity, or at least equal the applied bending moment. Okay? The capacity of the beam has to equal or exceed the MF. However, here there's a statement here. It says, this statement, that the way mathematically it's written, is very subjective, because MR can be twice or 3 or 10 or 20 or 100 times more than MF. And what does it mean? It means this is called over design. It's overkill. If I make my beam can resist 400 and my moment that come from the load is only 100, it means my beam has 4 times the MF. So this is very subjective, and this will lead to waste of material. I'm going to add lots of rebar in my beam. I'm going to, make my beam super big. I'm going to use a stronger concrete for no reason, because the loads based on my calculation is very little. The moment is very little from my loads. Okay, and that's why always, guys, whenever you see MR, I can simply replace the MR by MF. Okay, or I can replace the MR by MF, which means when I start my design, I need my beam to resist 100 kilonewton, and for my design to be safe, so the beam capacity has to be anywhere from 100 and above, but I will always start from the 100. Why this assumption? Because this will simply yield to or result in an economic design. I'm trying to match exactly my beam capacity with my applied bending moment. Are you following? Okay. Now, so what happens in my design? I'm going to always start from this assumption that my beam capacity should be equal my MF. And what happens, you'll see along the way from this assumption until I finish my design, I will make sure that this will never happen. Okay? See this assessment? I'm going to make sure along the way that my moment of resistance, or the capacity, will never fall below my MF. So you can see in red, is not happening, And I will see this every time I will do that. I will just, emphasize that in my design. Now, anybody loves math? Anybody enjoyed when we came up with the quadratic formula? I think
No.
one person only, Diego. Domenico. Oh, sorry, Diego. Diego, I think he enjoyed so much the math in the compression failure. Anyway, again, look at this. If you are not really into math, you can take a little bit of nap, and I will wake you up in a couple of minutes. Okay. So guys, there is a small derivation. There's nothing super. It just that I'm trying to use. Look at this. So I said here is this slide. You can see this slide here, which is simply nothing super. Sigma fx equal to 0. Sigma moment equal to 0. I will just do a little bit of math to come up with my area of steel. Please watch this. So I started here from T equal to C. Total tension in my rebar equals to total compression in my concrete. And from that, I went and I got this equation here, which you guys, if you finish assignment number 3, then you've done this 2 times at least. Okay? And then what happened is, I'm going to write my equation, my MR, one more time. Guys, remember, in the check problem, if you've done assignment number 3, you've seen this equation here. So this equation, it says the MR is equal to T multiplied by lever arm. Nothing new. All I did is I replaced my MR by MF because that's what I know. And then on this, what happens here, everything from this point on is math. So what I did is I simply, in this equation number 2, so let's say this equation number 2, okay, I replace the value of the A from equation number 1. So this equation number 1, so I took the value of A from equation number 1 and I substitute. You can see here is my arrow, so I kind of put here is take all this value, put it here. So nothing super. I came up with another equation called equation 3. Equation 3 is kind of a nice equation. Look at this and look at the way I color it. Please look at the way I color it. And please go one term by another term. When we start our design, do we know the MF? Please, I need to hear some noise, huh? Do we know MF when I
Yes.
start my design?
Yes.
Okay, the answer is my slide, but please, huh? And that's why you get no marks for that. Everything in green here, it means it's known. Anything it is in red, it is unknown. Anything in orange, it's kind of so-so, huh? Okay, so I want all of you guys to do this exercise. MF is known because we know how much this moment is supposed to resist. Phi S is constant. It's 0.85. Phi F sub Y, that's my rebar grade, which is 400. Area of steel, we don't know how much rebar is required, and that's what I'm after. I'm going to leave this for some time. I'll come back here soon, but you guys can imagine that alpha 1 is constant, is equal to 0.8. Phi C is constant, 0.65. F prime C, I have to start from reasonable assumption of F prime C. The width of my beam is also known from the architect or by the engineer. And phi S is constant, 0.85. F field is 400. And one more time, AS is unknown. We don't know how many rebar or what is the bar diameter, so AS is unknown. How about the D? The D, you can see I did not color it with red or green. It is somewhere in the middle because you can see the D, if you remember, the D is connected to my H and my D prime. Part of the D is known, which is H, but the other part, which is D prime, is unknown. So you can see the D prime is kind of a mix, nice mix between known and unknown. And that's why I'm gonna give you my golden rule. So the golden rule is here. The golden rule is here. You can see one more time, I'm using the same color. So I said here, the effective depth in orange is equal to the H, which is known, minus D prime, which is unknown, because I don't know how many rebars and I don't know what is the bar diameter. So I said here, D prime is assumed to be 70. So in my design, I will assume for 70. And you can see I'm explaining why 70, to compensate for concrete cover, stirrup, and then half bar diameter. It means I'm assuming here it is one layer of rebar. And this assumption I said here will ease future calculation or further calculation. And you can see this will be very difficult mathematically if I keep my this D here unknown. Very difficult mathematically. However, once I assume that my D prime is equal to 70, you will see how easy my life will be in terms of math. So I said here, this will ease further mathematical manipulation. However, it must be checked. And you can see in red, bolded and underlined. It means before you finalize your beam design, then we have to go back and make sure that this is happening. Okay. Now, once we do that, let me go back to here, guys. Please let me ask you. When you think about this equation, if I make the assumption that D is equal to H minus 70, so which means I can turn this into green. I can make this D into green. Now, how many unknowns so far? How many unknowns so far? Anyone's following in this equation? How many unknown?
One.
One.
One. Thank you. Now, what is the shape of the equation? Is it first order or second order? Take your time, huh? Take your time. I know you have to do some math work to kind of reorganize it and arrange it, but I think if you are good at math, you will know whether this is first order or second order or third order. What do you think?
I want to second order.
Who said that?
Mehdi.
Mehdi, why Mehdi, they say it's second order?
Because we have AS multiplied by AS twice, so we get a second degree, right?
Okay, sure. I'll give you a couple of marks for that. Thank you so much. Okay, guys, as Mahdi said, he looked at the equation very simply. He said, you know what? We simply have to take this S multiplied, this whole term multiplied by D, so we get first order. We take the same term one more time, multiply by this guy, so we get AS squared, okay? So AS raised to the power 2, which means second order polynomial. How do we solve second order polynomial? You don't have to worry about this one. I did the effort, and I'm giving you the final answer. So guys, here is the final answer. This is the solution or the positive root of second order polynomial. Please, I'm not going to waste your time to find what is the A, what's the B, what's the C. Just like the other class, I give you here the final answer. The final answer is your area of steel should look like this. Okay? Now, obviously, without any thinking, everything on the right side is known. Everything on the right side is known because simply we have only one unknown here, everything in green. So I didn't color it here, but you can imagine, huh? All those are known. Everything on this side. Now, let me think about this equation. And so this equation has alpha 1, phi c, and so on. And remember, the alpha 1 and phi c and phi s and f field, what do you think about those numbers? Those are kind of constant, huh? Kind of constant. So we can simply go ahead and we can replace every alpha 1 by 0.8, every phi c by 0.65, every phi s by F field by 400, and guess what? We get this very nice simple equation here, okay? And this is what I want you to know. Again, time now to wake up. If you have been sleeping for the last 5 minutes, now time to wake up, okay? We've done all the derivation, and you are not required to understand the derivation. You are only required to simply understand this equation and how do we use it, okay? Are you guys following? I need to hear some noise.
Yes.
That's it?
So, sir, so every time we would like to find for our AS, so we just have to plug into that equation.
Yes, sir.
Okay, thanks.
Okay, now, so right away, because we have 13 minutes, and all really what I want is to see this equation in action, huh? So really, I'm not going to finish today. We're only at slide number 7, and we will finish tomorrow, or maybe proceed on the same slides tomorrow. And so really what I want to do between now and we finish the class, we want to go ahead and try to use this equation. So here what I did is I give you a numerical example where I give you concrete dimensions. You can see that here. Huh? So here is my H is equal to 900 mils, and then 450 for the width, and concrete is 25 MPa, and you can see the same parameters, the same, huh? Alpha 1, phi CF, phi S, F field, same thing, no change. The new thing is, here is what my beam is supposed to resist. So my beam, when I finish my design, it's supposed to resist the MF of 800 at least. For sure, we will make sure that MR will be more than 800. So the minimum is 800, and we're trying as much as we can to be very close to 800, because if we do it 700, it's unsafe. If we do it 100, 800, we're safe. If we do it 2000, it means we're safe, but we're over designed. Are you following? So three things could happen. If we make our beam 700 to resist 700 or capacity 700, that's unsafe. If my beam is able to handle the 800, great, thank you so much. You are the best engineer because you're not wasting the material, and then you're making concrete strong enough to resist the load. But if we're making my beam to resist 2000, it means we're overkill, we're over designing our beam. So my beam is safe, but we have wasted a lot of materials. Okay. Now, other things we need to know is aggregate size, 20 mils. Concrete cover is 30 millimeter, and we're using 10 M stirrup, and my beam is exterior beam, and you will know this not today, next class, why I'm saying my beam is outside beam. So what we have to do, guys, here is we say the start is, you can see my equation, obviously, it doesn't use H. my equation, you can see it uses D, which will make sense, huh? Both check and design, both they depend on D, not H. We don't care the H, but we care the D, and that's why it's called effective depth. And that's why here what I do is I go ahead and say, okay, you know what? Easy, easy. I'm gonna go ahead and use 900. I will subtract my 70. So they look at this 70, and this compensates for concrete cover plus stirrup plus half rebar. Okay. Again, that's not Bible, huh? It's not 70. It can be 70, can be 60. Just an agreement. It's a reasonable assumption. And please don't use, like, for example, 300 millimeter, huh? Don't say 900 minus 300 millimeter, because simply that's too much. So be reasonable when you assume. To make my numbers on my exams and assignment the same, please use 70. So that's an agreement, only agreement. But nobody says you cannot use it as 65 or 80. Okay, as long as it's reasonable, then it's okay. But please, let's agree 70. Now, what happened is we got 830. Remember, I'm asking you, this 830 here, is it D actual or just D assumed for now? Please
An,
speak out.
an assumption.
Exactly. For now, that's an assumption. And you will see how easy, once I make this little assumption, you will see my life is super easy. I can find my area of steel. Let's do that. Now, you can see all you have to do is use the final equation after the revision. And to be honest, I want everyone in this class now to do it. You have the final answer here on my slide, but please use your calculator, because you can see the math has a square and has a square root and then bracket, and so it's kind of messy. And the only way to understand the formula is you do it yourself. So please right now do this line on your calculator. Please make sure you get 3,134. It's going to take like a minute. Go ahead now and thumbs up if you are able to get the same number. And that's for yourself, not for me, huh?
Sir,
Uh-huh.
that area of steel is a total area of the steel, right?
Yes, it is, of the main reinforcement.
Yeah. So should I also make assumption on how much the diameter of the bars that I'm going to use, just to
Not,
divide the
not for
total
the moment,
area?
not for the moment. Please just do the math, because this is another step that's coming soon.
Okay.
Anyone got the right answer? Thank you, Hamid, Rudy, Nico. Thank you. Gord, Henry, thank you. Really, it's very important. When I remember, like, I've been teaching this now for 7 years, so, and then 2 semesters per year, so that's number, let's say 13 or 14. I know exactly what I'm saying. When I ask you to calculate, then it has a necessity, because the math, you can see there is a square root, there is a term, there is a bracket, so you need to make sure that you got the math right. Okay. Now, last thing before we finish the class for today, you can see here, 3.1, please read the statement. It says here, whatever you get the number here, that's the minimum required area of steel to resist MF. That's minimum. It means, can I add in my beam 3,100? Can I add 3,100? No, you cannot add 3,100, because simply 3,100 will give you moment MR less than the 800, which is MF. So you need to make sure that you add area of steel more than this number. Otherwise, your beam will fail. So we cannot provide, remember also some other information is, we cannot provide exactly 3,134, can we? We cannot provide exactly 3,134. Can we? We can't, because simply we have to choose from standard bar diameters. We are not fabricating rebar as we wish. There are some standard bar diameters starting from 10M all the way to 55M that we have to choose from. Okay, so the actual area of steel has to exceed the 3,134 millimeter square to ensure that that MR, which is the moment of capacity of your beam, or the capacity of your beam, exceeds your MF. And that's exactly what I said here. I said here, guys, I said here, this is not happening. Those are one of the things I do. When I choose area of steel actual, it has to be more than the minimum area of steel by the equation. Okay, and we will do a lot of things along the way to make sure that my beam has insufficient capacity more than applied load. Guys, so far, do you have any question? Gord.
So with that 3134, it works out to either 6.2 25M rebar or 10.4 20M rebar. What would you pick? Would you go the 11 of the 10M or 7 of the 25M?
Sir, do you see my screen?
Oh,
that's the next slide, which will not happen today. So in the next class, I'm gonna give you all the options, and I'm gonna have the discussion. It's a long discussion, not short discussion. All of them, they are safe. However, there are some is favorite and some is bad. So let's run discussion tomorrow at 1 o'clock.
Sounds good.
Great, thank you. Okay, by now, any other question, guys? Looks like there is none, and I will see you guys in 10 minutes in surveying. Thank you. Have a good day. Or have a good surveying class. Thank you.